Now I would like to say a couple of words about friction or springs. So let me start first with the notion of friction. So friction generally occurs when a body is in contact with a rough surface. So far when we've sketched a box and analyzed the motion of the box, we have assumed a smooth surface, a surface which does not cause any friction. Now, if we replace the smooth surface with a rough surface, one can imagine that this would impede the motion of the box. And so one can say that whenever we're dealing with a rough surface, a surface that causes friction, this friction would oppose the direction of motion. So if we want to draw the force, it would simply be opposing the expected motion of the box. And so if the box is moving in the horizontal direction, the friction force would also be in the horizontal direction, but in the opposite sense. And in general, the friction force is equal to mu k times n, where n is the normal force, the force that opposes the weight, and mu k is the coefficient of kinetic friction. And so this equation applies whenever we assume that friction resists completely motion. So the friction generated by a rough surface here is assumed to completely impede motion. So the box is not able to move. And when that occurs, the friction value is equal to mu k times n. Now what happens when the box is about to move? And that's when the force is actually strong enough to face the friction. And in this case, one needs to replace mu k, which we have said is the coefficient of kinetic friction, with mu s, which is the coefficient of static friction. So instead of ff equals to mu k n, one now has ff equals to mu s n. Now what about mu k and mu s? Well, those two values depend on the surfaces we're actually dealing with and can be obtained from tables that are available in the book, or they might even be given in the problem statement. So to summarize again what we have said, friction opposes the direction of motion. In general, the value of friction is equal to mu k n, and that's assuming that the friction force is strong enough to impede any motion. But whenever the box is on the verge of moving, or is actually moving, one needs to replace the friction value to mu s n, where mu s is the coefficient of static friction. Let us now talk about springs. So let us imagine a box which is attached to the wall through a spring, which is initially relaxed. Now if we stretch that spring a certain distance delta L, we know that whenever a spring is being stretched, it would develop a force. And the value of this force is actually equal to K times delta L, where K is the stiffness of the spring and delta L is the displacement from the rest position. And so if one needs to write that down, one can say that the force is proportional to the displacement from the rest length and not the displacement from the initial state, whatever that initial state is. So if one needs to write formally what delta L actually is, well, delta Li is equal to Li minus L0, where L0 is the reference or the rest length, and Li being the length at state I. I have seen many students make mistakes when it comes to calculating delta L, so I'd like to illustrate the idea I've just demonstrated here with an example. So let us imagine state 1, in which the spring is actually stretched by a distance Li1, and so a force Fs1 will develop due to the stretch. And now let us stretch further this box to state 2, in which now we're actually looking for Li2. Now most students at first would simply say that Li2 is equal to the difference between the length at state 2 and the length at state 1. But that's wrong, because we've said that Li2, or any Li, is equal to the final length at state 2 minus the rest length, which is L0. So the actual Li2 would be the distance between the L0 reference and state 2. We do not care whatsoever about state 1. The force that's being developed is irrespective of whatever state the spring was before. It actually depends only on the rest length of the spring. and the rest length of the spring is L0. There's no room in the equation for delta Li or Li for the previous state. So you can see again in the equation for the spring, delta Li is equal to Li minus L0. There's no reference to the previous state, which here would have been Li minus 1. So remember, the force developed by a spring depends only on the rest length of the spring and the length of the spring at the state we're analyzing.